let's start today's answer and explanations with genetic problems. I gave you this 2 weeks ago. Yeah, there's extra copies over there if you need them. This is why I make extra copies. You'll notice that what I gave you, immediately what you should have done, which you may or may not have, is looked at the boldface terms and saw the definition of a gene, phenotype, genotype, law of segregation, law of independent assortment, different chromosomes inherited independently. All the definitions are right there on that front page summarized for you. And of course, we've gone over these definitions in class repeatedly. So you should have them in your notes. You have the definitions of phenotype, genotype, allele, locus, heterozygote, homozygous chromosomes. So before I go on and start using these words, does anybody have a problem with any of these words or either of these laws? They're over there. It says genetics. There's a lot of them. There's a big stack. You have to move them.
Is it a packet?
It's there's a giant. Somebody put them all in one giant pile. I don't know why.
I'm just an ordinary girl.
Someone pick up that poster. It's not a rug. Throw it away. Just throw it away. It's all ripped up. Thank you. All right. Does anybody have a problem with any of these words before I go on? We got to get going, so any issues?
No.
All right. Let's move on. So we all know how to do a Punnett square.
Yeah.
Who said no? Are you serious? What do you have? You've done your homework? You've paid attention in class? Okay, so what problem are you having with Punnett squares?
It's like I don't know which one to put inside the boxes.
Okay. Well, let's take a look at this first one real quick. It says here, complete the Punnett square of the monohybrid cross. What do we mean by monohybrid? By monohybrid, hold on a second. I want to switch a different color. I'll use blue. So when they say mono, they mean one gene. There's only one gene here. And hybrid just means there's two copies. So they just mean there's two people involved, right? Two chromosomes have been given. There's two copies of the gene. So you see here, there's 1, 2, 1, 2. Now these two are what? What are these? There's a dominant and there's a recessive. So what do we call those? What do we call it when we have a dominant and a recessive?
Oh,
That's right, heterozygous. Excellent. So if they use the word heterozygous, they mean for you to put down that there's one big and one small. So when you think about it, that means that this parent 1, has this genotype. How do you know it's a parent? Because they have two copies. And then this other parent over here has this genotype. This is the genotype, the types of genes they have. They're letters that represent genes on a chromosome. So if I were forced to give you like an example, it would be something like this, where this would be the gene. This is the place on the DNA where that sequences that protein. And there's one version that usually is called a wild type. Wild type is just the normal, what you find normally. And the other ones usually are called mutants, which are just different versions of the gene. And in this case, it's a dominant recessive version. We call those alleles. Now, before I go any further, is anyone confused about that? If you've done your Dragon Genetics and you've done your activities, which I have to get to grading today, I will be grading them, then I'm confused on how you did it if you didn't understand this. So alleles are different versions. So you have a big S and a little s. Those are two alleles. So mom has a big S and a little s. Well, what she's going to do is she's going to go through meiosis. And we don't have to worry about crossing over here because we only have one gene. We're only looking at one gene. Crossing over becomes an issue when we're looking at two genes. But we're looking at one gene. That means if this is mom's genotype, that means mom has a chromosome. What chromosome is it? I don't know. It all depends on how the scientists identified it. But one copy of the chromosomes has a big S gene, and the other copy of the chromosome has a little s gene. And for the little s, I'm going to put that little hashtag. Is everybody okay with that? You all nod, and then you tell me you can't do a Punnett. Some of you tell me you can't do a Punnett square. So ask a question if you're confused. And then the dad's chromosome is going to be the same. He's going to have two chromosomes. He's going to have two chromosomes, and he has one allele that's, dominant. The other allele's recessive. Which one is the normal and which one's the mutant? We can't tell. Do not get confused with this. A lot of people think that recessive means it's a disease. Because a lot of times when we look at recessive diseases, they're diseases that show up when you have the recessive gene. But not all diseases are recessive. Some of them are dominant. It all depends. All dominant recessive means, the only thing it means is that if you have the dominant gene, you see that phenotype. Is that clear? That phenotype could be good, it could be bad, it could just be no impact, right? It could just be how you look, not a big deal. Or it could mean disease. It all depends on the situation. So that's the parent. And you see here that these are the parents. We take the parents, we put them here. On the Dragon Genetics, you had the chromosome, like this. So which of these is going to end up in, let's say this is the father, and let's say this is the mother, which one's going to end up in dad's sperm? It's one of these copies will end up in a sperm. The other will end up in another sperm. Which sperm gets to that egg? I don't know. Well, which egg does the sperm get to? The egg that has this gene in it, this chromosome, or the egg that has this chromosome? I don't know. It's random. So how do we figure out the chances? Is we do a Punnett square. It's an easy way of doing it. So dad could give, it's a way of organizing the possibilities. So dad could give a big S and mom can give a big S. That's a big S, big S. Dad could give a big S and dad could give a little s and mom a big S. So that could happen. And over here, this could happen. And over here, this could happen. So what we get now is we get 3 different genotypes, right? These two are the same, and these two are different. So it's 3 genotypes. We have 3 possibilities. We can have a big S, big S. We can have a big S and little s, and we'll have 2 times those, right? And we'll have a little s, little s. Those are the possibilities. So what are the odds? What are the probabilities? Probabilities, not possibilities. Probability of getting a big S, big S. 1 out of what?
Huh?
The- one out of what?
Is it 7?
4. 1 out of 4. To get big S,
Oh.
the genotype. Now we're talking about genotype. Big S equals, the odds of getting that are 1/4. What are the odds of getting big S, little s? Equals 1/2. 2 out of 4, or when you reduce 2 out of 4, it's 1/2. Do we all agree with that? We're all okay with that? And then little s, the odds are what? The odds of little s,
1 out of 4.
1 out of 4. So that's for the genotype. There's the understanding that vocabulary that you all said you didn't have a problem with it. There's the genotype. That is genotype. Now the other word that, again, you all said you didn't have a problem with was phenotype, right? Now that's where you get, where your answers start to make sense. The one you started with was 75%, right? So I don't know what this is supposed to be. I didn't, did you guys should have finished this already. But here, if you notice in the question set, I already answered these questions, so I'm not going to go back. You guys can look at it. If you look at it, there's the word genotype, there's the word genotype, there's the word genotype, right? And when they say expected, when they use the word expected, they're looking for these values. These are the expected values. Does that make sense? The predicted values, the probability. Hear those words. If you're not hearing those words, you don't incorporate that vocabulary into your brain, you're going to get confused. All right? So hear those words: probability, predicted, the predicted value. In this case, they use the word expected. So when you see the word expected, and I don't like that they keep changing up the words, but they do. Expected means what do you predict is going to happen? What's the probability? So let's say big S is if you have a big S that equals big S anything, because it's dominant, means you're blue. And if you have a little s, then you're green. It's the only way to be green is to have a little s. Well, now we can look. Now that we know what the gene results in, we can look at phenotype probability. Now let's ask ourselves, how many of these that you're looking at this Punnett square are going to be blue? That's right. 3. 3 out of what? 3 out of 4. Or 75%. I guess I skipped a step, so maybe I shouldn't do that. 3 out of 4. When you divide 3 by 4, you get 0.75. When you take that 0.75 and multiply it by 100%, you get 75%. Does that make sense?
Yeah.
So that's 3 out of 4 is 75%. I always think of quarters. Do you guys still use quarters? All right, so I always think of quarters. If I have 1 quarter, I have 1/4, right? Or 25, correct?
Like
If-
math, we do math, and yeah, I use quarters in my head, but I don't use quarters like actually.
Yeah. As long as you have an image in your brain. So if you have 2 quarters, you have 50 cents, 50 out of 100, 50%. Right? If you have 3 quarters, it's what? 75 cents. So if that makes sense to you, hopefully that helps, especially since you have to do this on your math test as well. All right, so we're all good with this? Now how do we get this? Let's go on to the activity that I gave you while I was absent. All right. This was yesterday or day before, something like that. I also posted it. This was yesterday, I think. And I also posted it on your Schoology. Again, there's that homologous chromosome. Now we're going to look at crossing over because there's going to be two different genes, right? So it says read this. Do I believe you actually read this? I don't trust it. I don't trust. I mean, you're young people. Young people will try to skim. Let's read. No. I would never call you stupid. I know you're smart. You're a human being. And if nobody's going to be here, if the cat's away, what do the mice do? Yeah, they play. So alleles are different forms of a gene. We just said that, didn't we? So I think we got that. So I'm going to go ahead and check that off. And I don't hear anybody saying different. Genes are passed from parent to offspring. Alleles are passed from parent to offspring. Can be dominant or recessive. Well, they could be more than that. We should know that by now. Everyone should know that. You should have been doing your reading, and everyone here should know that there's dominant, there's recessive, but there's also codominant, and there's incomplete dominant. These genes are held on chromosomes which allow us to have traits. So there's that chromosome, the karyotype that we looked at earlier, all 23 pairs or 46 chromosomes laid out. And you just pick any one of them and you'll see there's a bunch of genes. This is a gene, this is a gene, this is a gene. And there's different alleles. Now, if these were homologous chromosomes, these would be copies. If this is mitosis, these would be copies. If this is meiosis, they could be different. These alleles could be different.
Each allele carries a different trait from the parent.
Each allele came from a different parent. So allele 1 is a version of the gene, and allele 2 is another version of the gene. So they're going to give you different traits, but they're different versions of those traits. But the genes control that trait. So let's look at some examples and think about it. If you're talking about skin color, green versus blue, like we just did, right? Then allele 1 would give you blue, allele 2 would give you green. But it can only give you green if you have two of them. Does that make sense?
Yeah.
All right. But they both control skin color. Is that are you hearing what I'm saying? So because it's the gene controls skin color, well, what different kinds of skin colors can you have? Well, it depends on your alleles, blue or green. In humans, there are 8 genes controlling skin color. And so it's not as simple as one or the other, right? It's a whole 64 different colors that we can shades of melanin that we can come in. Yeah.
Is this like based on what we learned Tuesday about the dragons?
Yes, the dragon genetics is exactly this. This is what I'm saying. Dragon genetics, everything's all the same. It's all the same. There's nothing. So far there's nothing new. How many traits are present? All right, so let's look at pretend the homologous chromosomes to the right belong to you. So these two are homologous chromosomes. Homologous chromosomes mean that they're the same number. So this is both chromosome number 3. These are your chromosome number 3s. And this is after meiosis. So you got this is the chromosome number 3 you got from your mom. This is the chromosome number 3 you got from your dad. Does that make sense? Yes? Okay. So how many traits are present? 3 traits, and trait 3. So they actually tell you. So the traits are here. How many different versions of the trait? Well, there's 2 for this one, 2 for this one, 2 for this one, right? So there's 3 traits. And where do you think each allele that makes our traits come from? Our parents.
Mom and dad.
That's right, mom and dad. How many alleles are needed to make up a trait? Two, usually. The exception is the X chromosome. X and Y chromosomes. That's an exception. I need you to know that because an X and a Y have genes that you only need, you only need one. Well, Mr. Mendoza, but don't girls have XX, so don't girls have two copies of each gene? Yes, you're right. Jimmy, you're so smart. Sure. Jimmy, you're just you're one of my most talkative students, and you're so productive. So yes, girls have two X's, Jimmy, and they do have two copies, but what they do is they randomly shut off one of the X's. They randomly shut them off by wrapping them up, right? One of the X's in every one of their cells. So they only have one functional X. They can't have both X's working because it doesn't work that way. So for the X chromosome, you only need one X, one working X. And that also helps ladies deal with inherited diseases on the X chromosome, and we'll get into talking about that on today when we go start looking at X-linked traits. Great job, Jimmy. It's such a wonderful transition. Okay. Alleles are passed from parents to offspring, can be dominant or recessive. Every trait needs to have two alleles in order to be expressed, except for X and Y. Letters are used to represent alleles to simplify. This means that two letters will be used to represent a trait. Dominant alleles are represented as a capital, whereas recessive alleles are represented in lowercase. In simple genetics, the dominant trait will always show up when present, which means the recessive allele hides in the presence of a dominant allele. That's how you can get a carrier. You've heard of this term carrier? They're a carrier of Huntington's. They're a carrier of sickle cell. Somebody can have sickle cell trait but not have sickle cell disease, right? Mm-hmm. That's someone who has the dominant allele, and because they have the dominant allele, you don't see the recessive allele. The person is what physically look like based off their genotype. Genotype is a person is based off of their genes. So this are the letters. Again, I gave you this because you guys were giving me those strange answers where you were confusing genotype and phenotype. I was hoping you would read this because it says, read this, and you would be clear that genes are the letters. You would be clear that the traits are determined by the genes. I was hoping that would this paper would clarify that for you. Okay, pretending that you received these two alleles from your parents, answer the following questions in complete sentences. So let's take a look at it. Here we have blue eyes. Here we have brown eyes. Which one's dominant according to what we just read? They're brown eyes. Here you have dark hair, and this is blonde hair. Which one which one are you going to see?
Dark hair.
So you are what? What are you?
Brown eye.
Brown-eyed, dark hair.
Smart gene.
Smart. Okay, you're smart, I guess. Doesn't exist. There's no smart gene, just for the record. All right, you're smart, and what else?
Tongue roller.
You're a tongue roller. There is a tongue. There is that. Look.
Okay.
Can you do that?
No.
I can't.
One of us is, I can't remember which one's dominant, which one's recessive, but I think rolling is dominant.
So, Mr. Mendoza, for genotype, we would put the letters. For phenotype, we would write out each trait. Right?
That's exactly right. For phenotype, you write out what you see. You see, you have the gene. You have, according to this, in this example, you have the genes for all the traits. You have the gene for blue eye and the gene for brown eye. You have the gene for blonde hair and the gene for dark hair. You have the gene for smart gene and the not so smart gene. You have the gene for tongue rolling and the gene for non-tongue rolling. Oh, wait, do you? No, you don't. You only have tongue roller. You're only a tongue roller. And tongue rolling is dominant according to this. So you have all the genes for all the traits except for non-tongue roller, correct? But what you see, your phenotype is brown hair, dark hair, brown eyes, smart, and a tongue roller. Are we clear?
Yep.
Okay. And that's what you would write here. Are we good? All right. And I'm recording this for anybody who's absent today. Now, this is also something I was hoping you would do. Again, thank you for that. I appreciate it. I got to be checked. You know, I get focused and I lose track of what's going on. So here we have, again, looking at a Punnett square. This is actually what the Punnett square does. When you looked at our Punnett square, I was hoping in Dragon Genetics, and I was hoping that when you did this, you could see this on your own. Did anybody see what's going on here? Do you see the connection between this and a Punnett square? Were you able to make that connection? A couple of the assignments had you look at that connection. I'm assuming that's a no, since I'm not getting anyone answering.
What? Could you repeat the question?
This diagram of meiosis and the Punnett square are connected.
Yeah.
Were you able to see that connection? In Khan, they talked about it. They talk about it in your book, in a couple of the activities. Some people are nodding their head no, and I'm not sure why, but we're going to go ahead and take a look at this. Anywho, use the diagram below to create sperm, right? We're creating sperm and eggs. The diploid is 2, which means that haploid number is 1. So diploid means you have 2 copies of each chromosome. Ploid means chromosome, remember? Ploid means chromosome. Diploid means 2. Only having 1 means it's a haploid, half the normal number. So these are all going to be haploids. Another word for these, oopsie. Another word for these, not going to work, huh? Let's try again. Another word for these are gametes. Gametes. They're haploid. Means a half the number of chromosomes. This would be 2n. N means the number of chromosomes. This is 1n. We take 2 in meiosis, just what we went over in meiosis. We went over it. I published a video, asked you to finish whatever you were confused. Come on Wednesday or Thursday. Today's Thursday. You can come today and ask me questions. Obviously, the test can't be tomorrow, right? Because I was absent. We all understand that? All right. So, let's go through the steps of meiosis. Well, this is what you start off with, 2 chromosomes, 1 from mom. Dad had 1 from mom, 1 from his mom, 1 from his dad. Mom had 1 from her mom and 1 from her dad, correct? Then they duplicated it. They went through S phase, remember the cell cycle, G1, S phase, G2. They duplicated the DNA. What does it look like after duplication and right before meiosis? What do they look like?
Would it be sister one?
Dad's chromosomes would look, from his dad would look something like this, right? They'd be doubled. So it'd be 2 of them. They're copied. So both of them are copied. I would encourage you to draw this out several times so that you know what you're doing when you're thinking about meiosis. People that get confused often haven't put the work in. Now, during this step, before the first division, you get crossing over. Crossing over doesn't matter in this case because you're only looking at one gene. It doesn't matter for our results. But it will matter if you're doing a double, two genes, a heterozygote. So I'm going to go ahead and do crossing over, even though it doesn't matter. And I'm going to do it off here to the side.
So once you cross it over, it'll be big B, little b?
That's right. So when they cross over, they form a tetrad, they split, they break, their DNA breaks, and they switch some DNA. So dad's chromosomes will look like this now. Let me do it differently. And then when they split, they're going to split by homologous pairs. So what you'll get, in other words, these two sister chromatids are going to stick together, and these two sister chromatids are going to stick together, and they're going to separate by pair of chromosomes. In mitosis, they would split, the sister chromatids would get split. But here we're splitting the homologs. The copies stay together. So the copies stay together, but one of the chromatids got switched. So here we have a little b and a big B. Now, again, in this example, it doesn't make a difference, but I like to remind you that it does happen. Here's little b. Yeah. Is it time to go? Oh, man. And they get a big B. Could you please try to finish this and for homework and try to understand, try to come up with questions and look at how this is related to the Punnett square. Okay, so I'm going to continue it here and we'll look at how it's related to Punnett square. When we see that this gets split, when we split again through the meiosis 2, remember this was meiosis 1, the way we discussed it in class. This is meiosis 1, where you have crossing over, where the separation of the homologs are, the sister chromatids are staying together, where in mitosis, the sister chromatids split. The homologs don't separate, the sister chromatids separate. Here the homologs are separating. And finally, when in meiosis 2, it's very similar to mitosis, in fact, virtually the same, in that they align vertically and the sister chromatids separate. So you end up with a sister chromatid with a big B, a chromosome, because now they're chromosomes, they're not sister chromatids anymore. A chromosome with a little b here, a chromosome with a little b here, and a chromosome with, sorry, that's not right. And a chromosome with a big B here. So what you end up with, you still end up with 4 different gametes, but if you look, because we're only dealing with one gene, you know there's only two types of sperm here. Do you see that? These two are recessive, have the recessive gene, and these two have the dominant gene, right? Now, if we had 2 genes and we had crossing over, then there'd be 4 different gametes. It'd be actually 4 different with 2 genes, 2 different combinations of genes. And the same thing would happen here. I don't feel like I need to repeat that. So I'm just going to move this over here like this. Oh, that's not good. Like this. There you go. That looks confusing. Yeah, basically the same thing. If that's okay with you, I'll just leave it here and just say it's the same thing. So then the question then becomes, well, what? Yeah, but I don't want the video to show that diagram just floating there. So anyways, when these two are combined, which do you get combined? 2 big B's, 2 little B's, or big B, a little b? It could be any of those combinations. And rather than every time figuring it out, a Punnett square simplifies that. So when you write at the top in a Punnett square, big B, little b, these are what the parent has. that is the same as what you see up here. This is the same thing that you see. I don't know which one's the father. Oh yeah, here. It's the same that you have up here. What is it that the parent has to give? Because the only thing they're gonna give each of their sperm is what they have. Does that make sense? They can't give something they don't have. Then mom had a big B, little b. And again, she is only going to give what she has. If she was little b, then this would be little b. So on the axes up here, and the y and the x, these are what the parents have. So they could give one of the chromosomes as a big B to the gamete, right? Each, which would mean that you have big B, big B, or they could have a babies that are big B, or they could be big B, or they could be little b. So because they're heterozygous, you get the maximum, both parents are heterozygous, you get the maximum amount of variability, which in the case of one gene, turns out to be 3 different genotypes. There's that word genotypes. Genotypes, so the types of genes. So in this case, I hope you can see that how many different, what are the odds of getting a big B? Big B.
25%.
So 25%. And if you don't get that, watch the rest of this video, because in the beginning I go through how to get 25%. Then what about big B, little b?
Oh, it's 50.
That's 50%.
And then 25.
And then little b, 25. Now, where people make mistakes, let's go over and make sure misconceptions. Oh my God.
Pardon this interruption. In a moment, some of you may hear the fire bell sound. This is not a drill. It is not an evacuation. You can continue with classes as normal. We just need to test the system. Again, you'll hear the bell, but you do not need to evacuate. Thank you.
Okay, so when we look at these, at these 3, okay, these are genotype frequencies. And I'm going to tell you right now where one of the places people mess up is this difference between genotype and phenotype. Now, if you looked at this, there'd be no way for you to know what the phenotype is, because they don't tell you. There's nowhere here does it say it's blue or green or big or small or whatever. But if we say big B is the color blue and little b is the color green, now because it's dominant recessive, that's an easy thing to figure out. Now you got your phenotypic ratio. What about the phenotype? Blue. What is the predicted value? 75% are going to be blue, and what predicted value are going to be green?
5.
So that I think is relatively easy. So you have those predicted values. These are phenotypic ratios. When they say phenotypic ratios, they mean, before I go on and look at the different ways to say the same thing, because there's various ways to say the same thing. Let's first say that 75% is equal to 3 out of 4. Does everybody see that? Which is equal to that. So the ratio would be the fraction is 3 to 4, the ratio is 3 to 1, and 25%. The ratio is 1 to 4, 1 over 4, the fraction is 1 over 4. The ratio is 1 to 3. Does that make sense? 3 to 1 versus 1 to 3. 3 blue to 1 white, or 1 white, 3 blues, whatever it is, whatever you want to say. But it turns out to be 25% or 1/4. So that's, when they say phenotypic ratios, what they're asking for, and other words they'll use on test questions, is expected values. They'll ask you, what's the expected value? If I cross these two, what are my expected values? They're asking for the Punnett square results. That's it. Or if you're using the multiplication rule, the sum rule, then I expect that. So expected value, another word they'll use is predicted value. So that's another word they'll use there. What are the probability of, you can fill in the blank. Or they might ask, I don't think they'll ask this, but they might ask, what are the odds of? But these are different ways that different people write the same concept. The phenotypic ratios give you all that for phenotypic, for the phenotype, and of course you can do the same thing with genotype, right? Expected genotypic ratios with expected genotypic values or whatever. Are we all good with that? All right. Thanks to the one young lady who actually read the chapter, and her representative.
He's not my representative.
Okay, he stole your idea. I see. Well, whatever works, I guess. So, in any case, what we have to think about, and when we talk about X-linked, is ladies have two X's, and a gentleman only has one X. Well, if you had a big A and a little a, and you had, let's say a big A is dominant. I can't remember what is dominant or what isn't. Let me look. So let's talk about color blindness. I like that. I like colors. That one I know well. I was going to use Huntington's, but I don't think it'd work out well in the discussion. So color blindness. Color blindness is you have to have a recessive form of the gene. I'm going to put a little hashtag on the recessive C, on the lowercase c. If you have this, you have normal color vision, average color vision.
Both are recessive?
What'd you say?
Oh, nothing. I just asked if both are recessive.
No, the little dat. Oh yeah, good question. That's wrong. So I'm glad you said something. So the other's colorblind. So if you have two little C's, you're colorblind. But to be clear, the reason that you need two little C's is because you have two copies. Does that make sense? Because here, let me be clear on this. If you're a boy, wow, okay, I'll wait. If you're a boy, you only have one X, and by the way, the colorblind gene is on the X chromosome. If you have just one little C, again with the hashtag means little, then you're colorblind because you only have one X. However, if you have two, you're not colorblind. If you have two X's, you're not colorblind. Well, what happens is that in some of the cells, this one is wrapped up, all tied up, so it's not used. In other cells, this one's all wrapped up or tied up, so it's not used. So only one of the two is being used, which is why I said you're so close that half the genes are being turned off. You're right, but it's actually half the chromosomes are being turned off, so it's not randomly. So because it's random, about 50% of the cells will have the colorblind gene active, the other 50% will have the normal gene active, the wild type gene active. You two can stop pretending like I'm stupid, and I'm recording this, I'm gonna leave it on, and stop with the side conversation and listening to videos. Close your iPad. Like, it's insulting that you think I don't notice it. I actually, when I communicate to all of you, I'm actually looking at you because I'm actually communicating to you. And you think it's funny, but it's not funny to me. But I'll move on. I respect the fact that you disrespect me, and I'll move on. So the two get combined, and what you end up with is, as a whole person, as a whole. I'm just going to put a square because I don't want to deal with people saying it doesn't look like a human or whatever. As a, you know what? Let me use round for female and square for man. So as a female. As a whole person, you're not colorblind. And as a male, I'm using squares and circles because that's how pedigrees are, right? As a male, you are colorblind. And that's because you have just enough of expression of this gene to allow you to see color, where the male does not express it because they only have one copy. Ladies have a secondary copy that allows them to make the normal protein. If they're heterozygous, obviously if they're heterozygous. So it turns out that on X chromosomes, regardless of dominant or recessive, well, I guess dominant really wouldn't matter, but with recessive traits, you're more likely to get a recessive trait, the phenotype, recessive phenotype, for X-linked genes. What that means is, to remind you, because I truly believe some of you still don't know, X-linked genes means genes found on the X chromosome. So because men in humans and any organism that has this type of setup, because the male has the X only one X, you're going to see this trait more often in males than females. So if I looked at a pedigree, and just to give you a quick reminder what a pedigree is, and we're going to look at a real one in a minute. If I had a pedigree and I had two individuals that are marrying, that's how we would look at it. One is colorblind. Let's call this person here colorblind. So this male is colorblind, where the other person is not. We know what the great thing is, the wonderful thing is, if we know that it's X-linked, then we know the genotype of this person. It's X recessive trait Y. Where this person, though, we don't know. And we'll get back to that later. But what we expect to see in a pedigree where you have the X-linked trait, recessive trait, is that you're going to get mostly boys having it. You get a girl having it? Yes, you could. Yes, you can get a girl having it. But it's less likely. Let me read. But they're not getting it from the father. Why are they not getting it from the father?
The Y is from the mother. X is from the mother.
That's right. In boys, the father, it would be easy to say, it would be really, really, really treacherous. It's really treacherous, but it's very easy to say, well, that's because the father is giving them the colorblind gene. That would be incorrect. The father did not give these guys the colorblind gene.
Because the Y came from the father.
That's right, because dad gave them the Y. The Y comes from dad. X-linked genes, X-linked genes cannot be inherited by males to the female. However, the female will have an X that will have the lowercase or the recessive gene. How do I know that? Because what did dad give the female?
An X.
An X. Because dad has an X, and in this case, in this example, this dad has the recessive gene, and he has a Y. He must have given his Y to his boys, but he gave his X to his girl, so he gave her the gene for colorblindness. She doesn't have it, why?
But she has another X.
She has a second X. And that X must have come from mom, and that must be the non-colorblind version of the gene, what we call the wild type. So and because it's dominant, right, the female is not colorblind. Yes?
Can I see that one real quick?
I'd rather you not. Is it an emergency?
Yes.
All right, go ahead.
Mendoza.
Take the pass. Yes? It'll be what? No, this is definitely just regular. This is X-linked inheritance. There's no codominance because this is only one. You either got one or the other. Either you're colorblind or not. Codominance, you'd have one eye colorblind, the other eye not colorblind. Right? That would be, you'd express both colorblindness and non-colorblindness. Yeah.
If both the parents are colorblind, that would mean
If both the parents were colorblind, then all the children are colorblind. There's no chance for them to be not colorblind, unless they're not biological. They're biological children. All their biological children will have to be colorblind, unless there's a mutation in somewhere, but unlikely. So the X then here had to come from mom. So now you all of a sudden you know that this X must be X little c. And this other X will say X big C. Now that's really bad luck, and you might say, wait a minute. And here's my question to you. And this is what I want you to calculate. I'm going to pause here. I'm going to have you calculate it right now. What are the odds that and this is only one gene, so this should be pretty easy. What are the odds that these boys would all be colorblind? And this female would not. What are the odds that this would happen? Go ahead and calculate that. So 50% chance of getting a little C, and 50% chance of getting being a boy. So to get this first boy, it'd be 50. Now, if they ask you about the order, there's about 5 ways of getting 4 boys and 1 girl. So you'd have to add those odds in as well. But we're not going to do that. That's crazy. Is that fair? Because I tell you, there's more than one way to get 4 boys and 1 girl, right? I can get a boy, then a girl, then 3 boys. I can get the girl, then 4 boys. Does that make sense?
yeah.
So if I'm worried about the order, but assuming we're not worried about the order, then it would be 0.5 times 0.5 for this first person. Do you agree? All right. Then the female having that combination, well, there's a 100% chance that dad's going to give her that X. Correct? But it's a 50% chance that that she's a girl, so it's 0.5. And there's a 50% chance that she can get the little c. Do you agree? So you do that for every...
0.5 and 0.5 for her too.
Yeah.
For all of them, right? Why? Because look, it's a 100% chance that
Yeah.
dad's going to give her
An X.
this little c, X. It's a 50% chance that dad gives her an X at all. Because if he doesn't give her an X, then she's a boy.
Okay.
Does that make sense? So there's a 50% chance that she gives an X. That's where this 50% comes from. Does that make sense to you?
Yeah.
Then mom is going to give her an X. She has no choice. So does she give her the little c or the big C? Well, it's a 50% chance, right? 1 out of 2. So 50% times 50%. Why? Because it's and, right? We're using and. So she'd have to get an X from dad and get the X with the little c from mom. Now, if we wanted to consider that other possibility, it would just make it even less likely to happen, but we're not gonna do that. That other possibility is the order of them. We're not gonna worry about the order. There might be a problem on there where they ask you about the order, but that's just a headache. So 1, 2, 3, 4, 5, 1, 2, 3, 4, and then the last one's a 5. All right? So you multiply all those together. That's it. That's your answer on the odds of getting, of these two parents getting this outcome.
0.312 times 0.01.
Somebody want to do it, please? Just oh, you don't even have to put parentheses. Just put 0.5 times 0.5 times 0.5 times 0.5 times 0.5 times 0.5.
Just 1/4 the power of 5.
Yeah, you can do that. You can put 0.5 to whatever power or whatever.
Fifth power? 0.5 times 0.5 is 1/4.
It's a less.
Or one, yeah, or you can do it that way. 0.5 to the fifth
You want
power.
the answer?
But those are the two we had originally. You told us we were wrong.
I don't know what you're talking about. So the odds are I never told you anything, so I don't know what you're talking
0,
about. 0.0.
0,
Zero.
0, 9, 7, 6,
0, 0, can I see? 0, how many zeros?
3.
3 zeros, and then let's just say 9. Let's leave it at that. Percent. Is that percent or is that the
It's just
number?
regular.
That's the number.
So
So the percent
of-
is 0.09.
If you want the exact number, why don't you just put 1/1024?
1 over what?
That's how it's supposed to be though.
Why 1024?
That's it, in fractions.
1, 2.
The quantity of 1 over 1.
I'm not understanding what you're
Well,
saying.
they're saying that the quantity of 1 over 1024 is the most accurate representation of the odds, except for like
Yeah, just.
Oh,
if you write down all of those.
yeah, I was just going percentage, 0.09% chance of.
Yeah, I thought that those genders at the bottom were given. I thought it was just about the.
Yeah, no, the genders are given, but the question, the order, if you consider the order of the genders,
But we're not
but
considering.
we're not going to consider that because that would just be insane.
So you just have to.
We know that this is the actual. Not. Hey, could we pause for a second? Give me another 30 seconds here because I got a whole minute, but I'm going to ask you for 30 seconds. This is the actual outcome. So when you're doing chi-square, this is the observed, and this is the predicted. So the predicted would be 0.09% to get this outcome. Does that make sense? Because you predict that. So when we're talking about what are the odds that this, what are the chance, what's the probability that we would get this, we predict this. If we see this 100% of the time, then something else is going on. Right? So if we look at 100 births and we see, if we look at 1,000 births and we see 9 families out of 1,000 that have 5 kids come out, they have this combination come out this way, then we're spot on. If we get 100% of them have this, then there's something else going on. All right?
Like, are we still typing this in?